This is a video to go with the code versus cost entry, and I wanted to do a little bit more explaining than what I did just in the written part of the entry. And this concept originally started with the entry on structures. And in the entry on structures, I start off by talking about why size matters. And I measure size of code in three ways: code size in lines. Then I use AVR size command, or make size if you're using my make file, to tell me the program size in bytes and the data size in bytes. Now, if we're talking about the first one, code size in lines, it's not an absolute number that I'm looking for. It's how do I add more of the same thing? How many more lines does it take to add more of the same thing? And so if you take a look through the structures entry, it breaks it down into where at one point in time, for every LED that you want to blink, it takes 5 or 6 lines, which is a lot, not a lot, but it's enough that if you had to add 10 LEDs, you're going, okay, this is kind of repetitive and ripe for error. And I boil it all the way down to using a struct in an array such that for every LED you want to add, it's simply one line. So I go from 42 lines for 2 LEDs and 48 lines or 49 lines for 9 LEDs. And if I wanted to go to 20, I just add another 11 lines and that would take care of those LEDs. That's the important aspect of code size and lines. It helps you understand the maintainability, the debugging, the feature enhancement aspect of your program. Okay, so then program size in bytes and data size in bytes, those aspects are rigid. Those are physics. In other words, if your program size won't fit in the amount of flash on that microcontroller, that program is not going to run. If your data size, which is the amount of RAM required on that microcontroller, is exceeded, that programs might run, but it's going to crash. And so you want to make sure that you're looking at those things for two ways. One, will I be successful? Or two, and this is where I get in code versus cost, do I have the ability to reduce the cost of my project because I'm vastly over investing in the hardware side of the equation? And that's what engineering is. Looking at that equation of code versus cost, or one aspect of engineering, and understanding, oh, I can reduce things. And so if I go to the code versus cost entry, I have the same discussion of why size matters. We've gone through that. And then I walk through a really simple example. And I'm going to do it two ways in the video. I'm going to walk through it in the entry in the video, and then I'll walk through it another way. But essentially what I do is I say I've got this 9 LED device widget, and I can make a persistence of vision device out of it, and go and look at the persistence of vision Arduino entry that I referenced there, do a search on POV devices. It's pretty interesting. And essentially you spin this device around your head or through the air, and it can spell something or make interesting designs because of the way the LEDs are blinking and the movement of the device through space. So that's a POV device. We have this widget, 9 LEDs, and the requirements are right here: 9 output lines, 2K bytes of flash, because I have a requirement of 1458 bytes of program storage, and 73 bytes, so I round that up to a power of 2 of 128 bytes of RAM. And so now I'm looking for 9 output lines, 2K bytes of flash, and 128 bytes of RAM. And I start off by saying, let's do this in a DIP. And the DIP is a dual inline package. It's what you see on the Uno 3. It's the one that fits into your breadboard. So we could breadboard this by looking at the DIP. And so then I do a search. And let me go ahead and get this out of the way. So then I do a search on DIPs. And the first one I see is $1.22. And I think, wow, that's great. And then I go across and I realize, no, it only has 1K byte of program memory and I need 2K bytes. It only has 64 bytes of RAM and I need 128 bytes, and IO, yeah, six lines of IO. So I can't use this $22 device. Now, what I've also want to point out is that um, it's not showing up here, but the I also show you the cost of the 328 P-PU, which is the dip version. One, you can't get it, but two, I think it's around $3.20 or something like that, and so it's really expensive, and it's also overkill. It's got 23 lines of I/O. It has 32K bytes of flash and 2K bytes of RAM. So it's way overkill. And so what I end up doing is finding this board, the 44, this one right here, the 44 PU for $1.66. It's a good price. It has 4K of program size, so that's good. It has 12 lines of I/O, so I could even expand it to 3 more LEDs, a total of 12 LEDs. And it has 256 bytes of RAM, so I clearly have enough RAM. Now, one more comment on RAM storage is that you always want to make sure that you have more RAM than less, because RAM is used for stack. The RAM is used for calling a function and returning from that function. That's where it stores all the variables locally. And so if you run out of RAM, your program crashes real time and you're not sure why. And so that's another caveat on RAM. So I found a device for $1.66. Now, what's interesting is that, let's say I prototype this and with this $1.66, and I make 100 of them, and each one costs me, $6 or $7, but I test it with 80 or so people. They all love it. They think it's fantastic. Now I want to make 1,000. And so I can go and look at this, and let me look at a different page. That's not the page I wanted. This is the page I wanted. And this is looking at it from a cost of 1,000 pieces. And I take a look, and this is also a surface mount. So it's going to reduce the size of the board. And it's going to reduce the manufacturing cost, because surface mount manufacturing is somewhat cheaper, and it's a higher volume, which also reduces the price. So now I have this ability to look for a device. And if I go down to here, because I'm looking for ones with a fair amount in stock, I can take a look at this ATtiny 402. And it has 4K of flash. Great. Only 6 lines of I/O. Okay, so that's not going to work. So let's keep scrolling. Here's one. Here's 8,000. 12 lines of I/O. 4K flash. 256 bytes. So that's the 404 as compared to the 44. It is a surface mount device, 8,000 in stock, 58 cents. So it's 90 cents less than the dip device. And so when you're going through this, if you're trying to roughly figure out what the cost of your goods are, I would take the cost of the microcontroller, which is 60 cents. Then I would add another 60 cents for the board and manufacturing. So that gets you to $1.20. And then I'd quadruple that for selling it to pay the selling costs and all the other things that you've got. And so if I had $1.20 and I quadrupled it, it's now $4.80. So I could roughly sell it for $5. And that's that whole discussion there. That's the engineering side of software development. And that's the point I wanted to make on the entry. So thanks for listening.